let's start the last topic of this unit number 2, rigid bodies rolling without sleeping. So here we have to consider a case of again rigid body, and in this particular case we are rolling the rigid body without the effect of sleeping. So when a rigid body is rolling without sleeping, then such kind of motion is the combination of the linear motion plus rotational motion. And here the center of mass of the rigid body is performing the translational motion, means linear motion, and the body itself is performing the rotational motion. So such kind of motion can be explained with the figure which I am going to give you. So here the rigid body is shown, which is rolling on the surface without sleeping. Now, as we have discussed, this kind of motion is the combination of two. So here both the motion can be studied independently. So let's try to study each kind of motion. So here the rigid body is shown, which is rolling over the inclined plane of height h, and the angle is, means the inclination angle is given by theta. Now the mass of the body, means the rigid body, is small m, and moment of inertia is capital I. See, I am writing over here the linear parameter as well as the rotational parameter because it is the combination of both kind of motion. Now, here the geometrical radius is given by r, capital R, and also the radius of gyration according to the mass distribution is given by capital K. Now, when the body reaches at the bottom of the inclined plane, its potential energy decreases by mgh. See, it is given. And according to the law of conservation of mechanical energy, we can consider the potential energy is converted as there is an increase in kinetic energy. Therefore, according to the law of conservation of mechanical energy, the potential energy is converted as the kinetic energy is increasing. So, the kinetic energy of the body is equal to translational kinetic energy, because it is the combination of two motions. So I have to consider the kinetic energy in both the case and the rotational kinetic energy. Now remember, what was the kinetic energy in linear kind of motion? That was 1 by 2 mv square, and in this case it is 1 by 2 I omega square. And so, according to the law of conservation of mechanical energy, here comes the potential energy, that is mgh. Now, we know one relation, that omega is equal to V over R and I is equals to mk square. So substitute these two relations in above equation, and therefore mgh is equals to 1 by 2 mv square plus 1 by 2 capital mk square into v square over r square. And so now I am taking common v square from the right hand side. Therefore mgh is equals to m plus mk square over r square into v square by 2. So now I am making this v as object or v square as an object. So my equation will be, these two will come into this side, so twice gh and this mm will be cancelled out, into 1 plus, see, this k square over r square will be as it is, and here we have considered in the rigid body m is equals to capital M. So this m and the left hand side m will be cancelled. Now suppose if the length of the slope which you have seen in the figure in the inclined plane, if the length of the slope is small d, then what happens? Then the body starting from rest moves with the linear acceleration, and its velocity is given by v square is equals to twice ad. And from the geometry of that figure, I can conclude one thing, that, see, this is the distance, or this is the height, and I have to find out the distance d which is covered by this rigid body, and this h is in the vertical direction. So I can write down in the component form d is equals to h upon sine theta, and as v square is equals to 2ad, so instead of d now I am putting h over sine theta. Now combining equation number 1 and this equation number 3, so we will get a is equals to g sine theta divided by 1 plus k square over r square. And here the linear acceleration a, means the direction of a is along the inclined plane, and its value should be equal to the value of g along the inclined plane. But according to this equation, the value of a is slightly higher than the value of g. Therefore, the decrease in linear acceleration is given by g sin theta minus the value of actual acceleration, what we have proved theoretically, minus g sin theta upon 1 plus k square over r square. And from these two, I can make g sin theta as common. So inside the bracket, 1 minus 1 over 1 plus k square over r square. So let's simplify the bracket first. Is equals to g sin theta into 1 minus r square upon k square plus r square. That is equal to g sin theta. After taking the LCM, this k square plus r square will come in the numerator, but it will cancelled out with this r square. So in the numerator, only k square will remain. And so the final equation is like this. So this is the decrease in the linear acceleration due to the frictional force F acting on the rolling body. And so we can conclude one theorem, or we can say the law of conservation of mechanical energy as the work done against the frictional force results in the rotational kinetic energy and hence only even in the presence of frictional force we can apply, or we can use the law of conservation of mechanical energy. So it is necessary that there should be presence of frictional force whenever we are studying the rotational motion, and the value of frictional force, that means capital F, is now given by mg sin theta into k square divided by k square plus r square. Now, we know one more thing. The normal reaction means capital N is given by the horizontal component of the force, that means mg cos theta. And so, now I can deduce one relation between this frictional force as well as between the normal reaction. So, I will get the value of F over N is equals to mg into k square over k square plus r square into sin theta divided by cos theta, that is tan theta, and this F by m is mu s, which is the coefficient of static frictional force. And so the value of mu s is k square over k square plus r square, because the mg will be cancelled out, into tan theta. So this is the equation, and here the line on the surface of the rolling body, which is at the inclined plane, is stationary, and for that the value of coefficient of static frictional force is used. But one more thing which you should note it over here, that the value of static frictional force must be greater than or equal to. If you get common this k square, then the original equation will return again, 1 plus r square over k square to tan theta. So the value of mu s should be satisfied, then and then the body can roll down without the slipping. So after applying the value of mu s, the body can roll without slipping. And now we will see some special cases. So first case is for a thin ring. In the case of thin ring, the value of radius of gyration is equal to the simple radius r, and therefore the condition for that mu s greater than or equal to 1 upon 1 plus r and k are equal, so there will be also 1 into tan theta. Therefore mu s greater than or equal to 1 by 2 tan theta. Similarly, if we see the second case, for a circular disc, then here the radius of gyration is r upon under root 2, and with the help of this value, mu s is greater than or equal to 1 by 3 tan theta. Similarly, if you see for the solid sphere, and the well-known example of a solid sphere is our Earth. So for that, the radius of gyration is given by under root 2 by 5 r, and so the coefficient of static frictional force should be greater than or equal to 2 by 7 tan theta. So this is about the condition for rolling a rigid body without slipping, and this question can be asked in 3 marks. The full question without these special cases. So with this, our chapter number 2 is over.